Okay, let's begin. Ah, ah, ah. Okay, so this is officially the last lecture before before we before the presentation. So next week I'm going to spend two lectures for you guys to prepare the presentation and make sure that every group member come to the classroom so I can give you some feedback and see how it's going, because you have to be well prepared for the second presentation, because that's what I'm going to carefully look for the evaluation. So even though I checked some marks on the midterm presentation, I'll put more emphasis on the final presentation. So if you say didn't prepare well for the midterm, the first presentation, if you do it well on the final, I'm not going to take the count for the first one. But if you do poorly on the second presentation, then I'll check the midterm presentation thoroughly and then put some mark on it. So, and also on the final presentation, I'm not going to ask a lot of questions because there is no need to give a feedback anymore. I'm going to concentrate on the evaluation part. So you have to be prepared well so that you can finish in time, at most 10 minutes, and everything has to be well organized, well prepared, and well presented. Okay, so today I'm going to talk about electromagnetic theory and also the last project. It's about the game again. So it's going to be the application of Stokes theorems and divergence theorem we discussed last time. So let's talk about the electric field. So electric field is the vector field generated by a charge. So it's not about the moving charge. Moving charge makes the magnetic field. Now we're only talking about the electric field. So when you have two charges, they have forces between these two charges. One pulls each other. So the Coulomb's law says the force, the size of a force that applies to each charge, one charge, or each charge, is proportional to the amount of charge itself, and also it's inversely proportional to the square of the distance between charges. But let's think of this way. I'm not care about the amount of, or size or strength of the force between the charges. I only want to think of this way. If there is a charge, then it makes a kind of force field that if I put another charge on it, that it moves because of that force field. So assume that I don't put the second charge yet, only have one charge, and think about this kind of force field inside of this space. So that's our electric field. So it doesn't have a charge of the second charge. You only have a charge at the center or at the position where it's located in terms of U here. And still, everything is following the same rule, Coulomb's law, that it has the proportional constant and also inversely proportional to the square of the distance. So when you look at the position R, where your charge is Q, charge Q is located at U, the amount of force that the next charge will experience is this much. And the constant, we're going to talk about this constant later. Let's talk about in a different perspective. So what we are interested in is how much the charges generates the electric field. So if you're going to take the flux of this vector field surrounding this charge, it shouldn't be changing as long as the surface encloses this charge. The amount of total flux generated of the vector field generated by this charge must be same. That's called the Gauss law. And what it's saying is that, all right, so if we put two types of the closed surface enclosing this charge, one is S and the other is S prime, the amount of flux going through this surface of the vector field should be the same regardless of the shape of S and S prime. So I think you guys have learned this in the physics class. But let's put this in the mathematical settings. I want to prove this. How do you prove this? So think about the volume in between these two closed surfaces. That's called V. And divergence theorem says that divergence theorem says that the volume integration of the divergence of the vector field is same as the flux going outside of that volume. So the volume, in this case, what's the volume? What's the boundary of a volume? It's the surface, two surfaces, S and S prime. So there are disconnected surfaces because we're talking about the volume that is in the annulus part of the charge. I'm not talking about, so each S and S prime is the surface surrounding the charge, but not looking at inside of this surface. I'm looking at the volume in between these two surfaces. Okay? So when I try to take the surface integration of the boundary of this volume, the outer surface has the orientation going outward, but the inner boundary has an orientation that's going inward. Right? So let's forget about this orientation. I just want to take the surface integration, which is an outward direction for S and S prime. But then if I want to take that into a formulation of divergence theorem, I have to take the minus of the inner shell of this volume, of this boundary of the volume, because I need to change the orientation. So this is our surface integration over the boundary of the V, and this is the triple integration of the divergence. And if you take the formula of the electric field, which is R over R squared, R cubed, then the divergence actually becomes 0. So the integrand, everything is 0 here. So you're integrating 0 function, so it's always 0. So what it says is that the integration over the S and S prime are always the same. So it doesn't matter how much what the shape of the surface. And if you take any surface, nice surface that you can actually compute the surface integration, the total flux is actually given by Q over epsilon 0, and that is actually the Gauss theorem, Gauss law. And you can see that the total flux only depends on the charge, not the shape of S. So let's talk about this in a more detailed sense. I'll show you a picture also. So here's your charge, and here's your S, and here's your S prime. So I'm drawing in the two-dimensional sense. So our volume is the volume in between these two surfaces. Okay, this is our V. So if you take the boundary of V and take the orientation outward, then this is the outward direction of outward orientation of boundary of V. But however, when I take the surface integration, I don't want to I don't want to think about the volume surrounded by any two surfaces. I just want to look at the surface itself and then take the surface integration. So for this part of S prime, this is my orientation for the part of S, and this is my orientation. All right, so if I take the surface integration of the boundary of the V of the electric field, then I can split it into surface integration of on S and surface integration on S prime. But then for S prime, the orientation is coincide to the original orientation of S prime, but on the S part, it's inverse. So when I take the boundary of V, the orientation must be the outward direction of the volume. This is the outward direction when I look at the volume. But when I look at the surface integration, I can just think of this as my orientation of parameterization. So when I look at this, then this has orientation of n instead of the blue ones here. So I need to take the minus because when I take the integration here, I need orientation to be outward. So before we carry out the computation, so that's the left-hand side of the divergence theorem. The right-hand side says it's same as the triple integration over the V of divergence of vector field here. And let's try to compute the divergence. So it's assumed that our point of charge is at origin. So our vector field E is given as Q over 4 pi of x, y, z divided by x squared, y squared, z squared, 3 over 2. So let's try to get the divergence. So divergence means that I take the Q 4 pi, just constant, and I take the partial differential of x over something and up to partial differential of z. Let's take the partial differential on x and see what happens. So it's a partial differential of this, and you know how to take the partial differential. So we have q and x squared plus y squared z squared 3 over 2 minus x times 3 over 2 x squared y squared z squared 1 over 2 2x here. So there are many canceling out 2 and I want to cancel out this 1 over 2 to 5 over 2, and this becomes 1. So it becomes x squared y squared z squared minus 3x squared x squared y squared z squared 5 over 2. Did you guys do this computation in physics? Does it appear in physics? Have you done this in the physics course? No? Have you computed the divergence in the physics course? No? Okay, so yeah, so this is the partial differential, the first part. And you can see that x and y are symmetric. So you can see what will happen when I change the partial differential on y. This x only changes, right? So this part is the only thing that changes. So when you do sum up all the divergence here, it has the same denominator, 5 over 2, but it has a common thing here. So there are 3 sums. So these are tripled 3 times x squared, y squared, z squared, and then we have 3x squared, 3y squared, and 3z squared. So everything cancels out in the denominator and numerator, so it all becomes 0. So it means that in the volume between these two surfaces, closed surface, divergence is 0. Nothing goes in and out. Nothing is expanding here. So it's 0 on the right hand side, Therefore, it says it implies that the integration, the flux over S is same as the flux over S prime. So that's the Gauss theorem. Again, well, let's see. We only show that the flux doesn't depend on the shape of the surface. So let's actually compute the value of the flux. So I'm going to assume that my S, the surface, is the shell, spherical shell boundary of radius epsilon. So let's compute S epsilon of Q over 4 pi. We assume that the charge is at the origin, so this is the denominator, and the numerator is x, y, z, ds. So that's a total flux. So I can take out the Q over 4 pi, and you can take the parameterization of sphere and then do the computation again. And let me show you an easy way to do this. So I need to take x, y, z, and here, same thing. The orientation outward from the surface, n, and take the integration here. So what is n? We're looking at the small sphere of radius epsilon, so this is epsilon. And whenever we have a point x, y, z on that surface of small sphere, the orientation is in the same direction of the position vector to the xyz plane. So that's the only perpendicular direction, right? However, the size is different. So the vector from origin to xyz has a size epsilon. We need the orientation to be a unit vector, which is of size 1. So this n has to be rescaled from the position vector by epsilon. So that's my n. So let's plug that in here. So we have q 4 pi, and here x squared, y squared, and z squared, and 3 over 2. And we have x, y, z. And again, what is n? It's x, y, z divided by epsilon ds. And you can see what happens. So we have x squared, y squared, z squared, and it cancels out with this, the numerator, denominator. So actually the numerator becomes epsilon squared, and this is epsilon cubed, because every point x, y, z has a distance between the origin to the point as epsilon. So, so we have epsilon cancel out with this epsilon, 1 epsilon, and epsilon cancel out with this epsilon. So we have a 1 over epsilon squared, and then we're integrating the surface area of the sphere. So it's q over 4 pi, 1 over epsilon of the area, surface area of the sphere of radius epsilon, which is 4 pi epsilon squared. So it's q over 4 pi. Okay. I forgot to mention the constant here. So yeah, there's a epsilon 0 here. Epsilon 0. Epsilon 0. Not 4 pi, sorry. So it's epsilon 0. Okay. All right, so that's the Gauss theorem. And well, before I move on, is there any questions on how we derive the formula? Okay, no question. All right, so let's take a physicist perspective of Gauss law. So just think naively that we are taking a flux through the surface surrounding of charge, and let's apply the divergence theorem on that surface. So divergence theorem says the flux across the surface is same as the integration of the divergence inside of the volume surrounded by the surface. Now, I know that the flux is always constant over, which is Q over epsilon 0, but then it simply says that, okay, so if I take the integration of the volume of that divergence over the volume, then it's same as Q over epsilon 0. That's what physicists just make sense of this observation. Mathematically, it doesn't make sense. Mathematically, it doesn't make sense because, okay, so if you assume that the electric field is given by the formula that I just gave you before, like this one, that it's inversely proportional to the distance between the charge and the point, then if the point that you're looking at is same as the point of charge, then denominator becomes 0. So when you try to apply the divergence theorem, you have to have a condition that the vector field is well defined at every point inside of the volume. But in the volume, there is a charge where the denominator becomes 0 for the vector field. So it doesn't satisfy the condition. So mathematically, you can't apply equality here. However, what physicists think about this as is as follows. So assume that the volume is very small, almost like a point. Okay, mathematically, the volume never cannot be a point because it has different dimensions. But just assume that V is almost like a point. So if it's at a point, then the integration over that volume is just same as the same as that evaluation of this divergence at that point. So they think this is a divergence is equal to that equal to that total value Q over epsilon, which is the flux. So this expression is called the differential form of the Gauss law. So integral form is this one. This is the integral form of Gauss law, and you can also think this as a differential form of Gauss law. And well, in the physicist sense, in the first place, the reason why they put this vector field in this form is to make sense out of the law, right? So the law is first, not the formula, and the formula is made out of the law, so they can change the formula whenever they need to. So once they have this equality here, then they don't no longer care about the formula itself. They just mention that as long as it satisfies, it's fine. So they can assume that this vector field is no longer in that formula, that something that can be defined inside of the volume surrounded by the surface, so they can just do this way. So it could make sense in their perspective, but whenever you have a problem with the mathematical formula, then you have to find a way to explain why they are different. All right, so electric field is electric field, and sometimes electric field is also dependent on the magnetic field, because if magnetic field is changing over the time, electric field is changing. But in the magnetic field, it is always defined by the change of electric field. And more specifically, it's the field, the magnetic field is a vector field generated by the moving charge. So charge is moving to generate the current, and because of the current, you have a magnetic field. And Ampere's law says it's some version of the Ampere's law that if whatever the magnetic field is, so it's more, I think it's intuitive than the electric field. The magnetic field is something that's generated by magnetic pole over some magnetic pole, or the change of the electric field, or change the moving charge. But whatever that is, if you take the property is that, by definition, if you take the line integration along the curve, along the loop that surrounds a wire or electric wire, then that is proportional to the amount of current that is flowing in that wire. So that's Ampere's law. So in a way, it gives the meaning to the magnetic field. So it's not that you have a meaning of a magnetic field first and then try to think about why this is happening. So this is the definition of the magnetic field. Magnetic field is something that if you take the line integration, you get the amount of current. Now, let's think of this way. So this is also what physicists like to think of whenever they have this kind of situation. That we think of this wire as a thin wire. It has a volume, but it's really small, so we don't take what's happening inside of the volume, right? Inside of this wire. But instead of taking a thin wire, almost like a line, but you take entire space surrounded by the curve, or curve C, or somehow the cylinder parallel to that wire, so that you think the current is ideally flowing through the entire surface bounded by the curve. So instead of taking just one line, I take a surface bounded by the curve C, and I imagine that there is a density at every point in the surface, and if I take the flux through that surface of that density, current density, then it's same as the current I. So this J is called the current density, and it not only talks about the actual inside of the wire, it talks about the entire space filling in the side of the curve. So when you take that as a somehow big wire or big space that the electric charges is flowing, then this is how you define your current by taking the surface integration. And by definition, again, our magnetic field is something that gives the electric current by taking the line integration, but let's use the Stokes theorems here. So, well, there's no restriction anymore because we didn't define our formula yet, but so the magnetic field is the vector field filling the vector space, and we assume that it's well defined in every point. Then we can say that this line integration is same as the curl, a surface integration of curl that is over the surface whose boundary is the curve C. So I can identify this current is same as this, right? So now we also do the similar thing we did before. We assume that this surface or the loop curve C is tiny, it's really small. So we can assume that the inside, the integrand, is almost the same thing. So we can just drop the integral symbol here so that the curl of B is same as the proportional constant mu 0 times the current density J. So you can imagine that the kind of spin of this magnetic field generates the current J, because J is the current density. So somehow it measures how much the current charge is moving in some direction. So be careful that J is not a number, so it's a vector, because it's pointing to the same direction of a current. So you need a vector anyway. So that's Ampere's law in a different perspective, but there's another law or principle that describes the magnitude of the magnetic field. It's called the Biot-Savart law. And it's a little bit generalized Ampere law. The Ampere law only talks about the current loop. But here, instead of taking an entire loop, let's take a small segment of the current. So this is dI. So I is also a vector because it has not only the amount of flow of the charge, but also it has a direction. So I is the magnitude, dI is the vector. This vector notation indicates where the charge is moving to. And it says that the amount of infinitesimal amount of magnetic vector field
is given by this formula. So it's similar, but also we have a cross product. It's similar in the sense that it's inversely proportional to the distance, square of the distance from the point to the current. So by the way, the R is where we want to measure the magnetic field. U is where the electric current is, so electric element. So when you have this, let's plug that into the Ampere's law. So when you take the loop around along some curve, so that's the entire magnetic field experienced from the point R, or because of that loop. And this is how you get the calculation done. So this loop is loop for the electric current. So C is integrated. This integration is on the curve C, and then you're integrating over the variable U, not R. R is constant, so R is the point where you measure the magnetic field, and U is the point where you're moving your charges, like current. So that's how you take the magnetic field and compute the magnetic field. You can actually make, you can actually use this formula in order to get the actual amplitude, size of a magnetic field of a infinite wire or circular wire and so on. But let me show you in a more different perspective here. So instead of taking a line integration, let's take the surface integration or volume integration here. So I'm going to combine the situation where we have a line integration for the magnetic field and also this situation. So the current is defined to be the surface integration of the current density function, right? So instead of putting I here, instead of putting I, so I should be inside here, although the I is always just constant here, but in a real situation, I should put in here, like this one. I replace I by taking a surface integration of the current density, so it becomes a volume integration. So the Biot-Savart law says the magnetic field is given by the volume integration of these thing here. So instead of I, we have current density. So you can think this way. So you have a triple integration. 2 integration for surface integration, 1 integration for line integration. So surface integration gives the integration over integration of the current density to give I, the current, and then take the line integration with the current to get the magnetic field. So why we are doing this? Because I want to express the magnetic field in terms of something else. So let's talk about the Nabla operators. So far I used R and U independently. So again, R, okay, be careful about the R, so let me show you again. R is where I'm taking a measurement of magnetic field or electric field, whatever. R is the point of interest. I want to compute something on here, but U is where things are happening. So the U is the place where the electric current is happening, and that because of that I have a magnetic field. So, however, U and R is independent of each other. They're independent. So they're just the 2 different reference frames. So I can take this R and U independently, and R has a variable x and y and z, and U has a variable u, v, w. So let's take the Nabla operator separately here. If I take the divergence of this scalar function, so this scalar function has 6 variables here, but I can take one set of variable as a constant relative to others. So let's take R as a variable, U as a constant, then I get this when I take the divergence. So in the formulation of magnetic field, in terms of the triple integration, I can replace the R over R cubed part as the divergence of this function. Okay? This is something that covered in the Physics? No? Okay, so look at carefully. So we have this, and well, nothing changed yet, right? So I'm going to express in different wording here. So remember that we had a formula identity between these two. So if you have a vector field multiplied or scaled with the scalar function f, then you take the curl, you have this reformulation of function here. So I'm going to apply this by substituting the vector field f by j, the current density, and small f to be 1 over the distance. So here I have small f and vector field f. That's what goes here. And on the left and on the right hand side, I have these two. But look at carefully what we had before. So we had del f cross vector field f, right? So this is exactly same as this part with a minus sign here. So if you change the order of cross product, you get rid of minus sign. So del f cross f is what we had in the first integrand. So the first integrand, the formal formulation can be represented as this one, which is on the left hand side, minus this part, minus this part. So what did this part says? So remember, small f replaced by 1 over distance, large vector field f is the current density, but current density is a function of u. Is a function of u. Okay? So nothing about r. So it only depends on where the current is flowing. But we are taking, so actually there is a but this is also true, but what I want to mention is the cross product as a curl. So when I take the curl of the current density function in terms of r, I'm taking a partial differential in terms of r, and everything becomes 0 because current density has nothing to do with r. Okay, so it's all 0. So this part, it goes 0. So what is left is this, right here. Okay. So therefore, now let's take out this the curl symbol outside, because even in the inside, the integration is about u, not r. So I can just take out this as something that I can apply independently to the Riemann sum here. So I can take out everything here. And it simply says the magnetic field is same as curl of something. Curl of something. So now this seems quite weird because you see, I'm taking a triple integration, and it looks like the triple integration is always giving me a value. Triple integration gives a value, right? But we are taking a curl of something, and this must be vector field. So what it means is that, so here, distance is scalar, j is a vector. So what I mean by this integration symbol is that I'm taking an integration in terms of x component, y component, z component of this current density vector independently to get a vector out of this vector field, out of this triple integration. Okay. So I'm just separating this j part into 3 pieces, and then do the triple integration separately, and then each component gives the component of the total vector field here. So then I'm taking a curl here. All right, so now I can consider this as a vector field, a new vector field. It's called the potential vector field, magnetic potential vector field, or magnetic potential, vector potential. So usually the potential simply means it's a real valued function, but because it's a vector, so it's called a vector potential. And now, a simplified version of this expression of magnetic field is that it's the curl of a vector potential A. And because of this formulation, if you take the divergence of the magnetic field, assuming that there is no change in the electric field, then it's always 0. So in some sense, it only happens when you have no pole, monopole, or dipole inside of the space. So as long as that happens, then your magnetic field is incompressible vector field. in mathematical wording. All right, so that's our Maxwell's equation summarized together. By the way, we haven't talked about when the electric field and magnetic field is changing over the time, but in general, everything is changing over the time. So the first one is Gauss law, it actually doesn't depend on time. But the second version, this is the Faraday's law, that if you change the magnetic field, then you change the electric field, or at least you give a force to the electric charge here, and or make current flowing. And the third one is a situation where you don't have a monopole inside. And the last one, I haven't discussed this yet, but maybe not in this lecture. So when you take the curl of the magnetic field, actually I discussed this, right? If I take the curl of the magnetic field, I get the current. So at least the element of the current density here. But also, it's only when you have no changes in the electric field. So if you have a change of electric field, you can have the flux going through some surface of the surface through the same surface where you have a current density. And then if you take that account, then you can have more term here. So I think I forgot the name of this theorem. So maybe this is the original Maxwell's equation. So this one is Gauss law, or Gauss law, Coulomb's law, and this one is what? Faraday's law, no monopole, and this is simply called the Maxwell equation. And there are many ways to formulate one to another, but so if you look at all the different texts, they have all the different notion of the expression of this Maxwell equation, but this is most commonly used way of describing it. So you can use the Stokes theorem. So the conclusion is you can use the Stokes theorems and divergence theorems to make sense out of these physical situations, especially electrostatic and magnetic static field. What we are going to do as a project, the last project, is to try to visualize the magnetic dipole, so not monopole, dipole. So what is magnetic dipole? So it means that you have, in some sense, like an electric dipole, plus and minus, so that you have a magnetic field that's going through one to another. And we assume that this is generated by a small loop of a small loop of current. So there is a dipole moment M, which is defined to be the current times the area element. The area is pointing to where the current is flowing. And the formula, so it's formulated in the vector potential here. So in the dipole situation, magnetic dipole situation, the vector potential is given as the following. So we have a point where you want to measure your vector potential, and the element where your dipole is at, U, and the M is the dipole moment. So it depends on this, how much the current is flowing. And you can see that it's actually inversely proportional to the distance here. And if you want to take the magnetic field, then you have to take the curl of a vector potential. So that's how you get the formula here. We'll derive this formula together shortly. And once you have this formula, let's pretend that we have already proved this formula is true. Let's try to make actual coordinate of this formula. So assuming that the dipole moment is pointing to the positive z-axis, 0, 0, 1, we can always do that because dipole moment is always in the constant direction, because you're assuming that the dipole is very small in the small segment of the wire. And the M is 0, 0, 1, and R is x, y, z, and the small r is just the size of x, y, z here. If you plug in everything, then the formula of your magnetic field in terms of x, y, z goes like this. So that's a three-dimensional picture that is your dipole is aligned in that direction. If you want to visualize it, you can do it on the 3 dimension. The easy way is to think about this in the 2-dimensional picture, and then everything is symmetric around the z-axis. But let's visualize in the xy plane. So in this case, z is you have to get rid of one axis here, but you can't get rid of the z-axis because z is something that you need to keep in order to make the dipole moment here. So get rid of x or y, it's the same thing because it's a symmetry. Let's say I get rid of x, so I get x equals to 0. That means I have no x component here. So this 3y0 and then 2z minus y squared, and in the below the y squared plus z squared to the power 5 over 2. So this is our formula. This is our code to find it's somehow flow line of the vector field, because you can draw each arrow, small arrow, to represent field, vector field. But here I use the stream plot, which is a nice function that is convenient to use whenever you try to give a curve, a trajectory curve that follows the vector field here. So in order to use the stream plot, I just made a grid, the lattice grid in the -2 to 2 window, and then I take the size of x and y coordinate of component of the vectors here. So x component is the y component of my formula here, and y component, the straight one, vertical one, is the z component here. And so when you see this formula, it doesn't make sense when you have x, y, z all equal to 0, because 0 goes to the denominator. So whenever x, y, or y, z are small, so that this makes a problem, then I don't want to make any plot. So whenever the radius between the origin point and xy is less than some threshold number, 10 to the minus 5, I made the size x and y component of my vector to be 0. So then the stream plot looks like the following. So you can, so it automatically sets how much the length of these trajectories and where the vectors are drawn in here. So it's a bit convenient to use. But what I made as a game is I will just show you the figure here. I'll just do it myself. I want to do it, do the streamlining myself, putting a dipole in here, and then you can see the green dots here is where the trajectory is starting, and then whenever I hit the enter or a space, then I want the streamlining to move in a direction where the magnetic field is toward along the magnetic field. And there's some stuff that I have put as a condition that if I put my green dot too close to the dipole, then so what I did, or how we're going to do it, is using the differential equation and then solve it by numerical method to find the trajectory line here. But if my point, the green dot, is too close to the dipole center, then the numerical solution goes a kind of weird way. So I set the plot to be not appear when it's too close to the dipole center. So anyway, so that's how we're going to do it, and then so let's try to first derive this formula, and then I'll show you how it looks like. So by the way, the code is complete code is here, starting from here. So you can just copy paste by yourself and then see how it look like, and then you can don't do it exactly the same, but get the idea what we're going to do in the last project. So let's try to let's try to derive this formula. By the way, so if you have any question, let me know right now before I do this. Any questions on the dipole side? Okay, so let's try to compute this one. So again, we're taking a curl in terms of x and y and z. So I'm going to, let's see, modify the formula a little bit. So R is x, y, z, U is u, v, w, and the dipole moment is the constant vector. So I'm going to write it as mx, my, mz. So let's expand the formula first. So in the denominator, it's fine. It's not hard. It's not hard. So on the numerator side, so u minus r is u minus x, v minus y, w minus z, and so m is mx, my, mz. So that's my u minus r cross m. So it's mz v minus y minus my w minus z. So I mean, there's no other way of doing it all manually. So this is mz u minus x minus mx w minus z, and mx v minus y minus my. So yes. No, it's opposite, sorry. So it's my u minus x minus mx v minus y. Okay, I think I made a mistake on the sign here. So let me make sure. So it's minus sign here. Okay. All right, so let's look at the first one. So what I'm going to do is take a curl of these vector divided by the size squared, cubed. So let's take the first computation. So the curl is the curl is rz, ry minus qz. So rz part, ry part. So I need r. So r is from here. So this is the last coordinate of the vector. So my u minus x minus mx v minus y divided by the size. So u minus x square w minus z square cube over 2. And I should take the minus of now qz. So mx wz. So this one, q is this one, minus mz u minus x, and then 3 over 2. All right, so let's do it all manually here. When I take the first one, it's something cube, and when I take the differential here, mx, and here 3 over 2, and we have everything, u minus x minus mx v minus y multiplied 3 over 2, 1 over 2, and the derivative of y, 2 times v minus y. Okay, so and then you take the minus of the second derivative, the similar thing here, cube. Now we have mx minus mx in this case, and then cube over 2, and mx w minus z minus w mz u minus x times 3 over 2, 1 over 2 times 2 times, so we're taking a partial differential in z, so we have w minus z. Okay. All right, so let's make a cancellation. So I have 2, 2, and I have 1 over 2, so I can get a 1 here, and then 5 over 2. And same thing here, equals 1, 5 over 2, disappears, 2, 2. So denominators are the same, it's 5 over 2. So in the numerator, so we have twice of mx of thing here to the power of 1. And in the rest of the part, let's make it this way. So we have my u minus x times v minus y plus mx v minus y square. And here you have mx w minus z square. So actually it's not minus, it's plus because we have a minus sign here. And then you have minus of mz u minus x w minus z. So we need a little bit of trick. So first I'm going to take these two, where? So v minus y is plus, right? So it's, yes. So I'm going to take these two, and combine with these, because it's the same thing. So mx, and here inside we have v minus y squared and then w minus z squared. So this becomes 2mx u minus x squared plus 3mx v minus y squared plus 3mx w minus z squared. And then let's take my u minus x v minus y, mz u minus x w minus z, and divide by something here. And then I'll do one more trick here. So instead of making it 2, so this is not 2, but let's make it 3, and then subtract 1 here. So then everything in here becomes 3mx times the square sum, and then the rest of the part is become u minus x times m inner product with u minus r. So you can see that the common term is u minus x, and everything is just the inner product of mn u minus r. 5 over 2. So you can imagine this is the first, so this is the x component. You can imagine the similar thing will happen for the second component. So second component will be 3my, the same thing, minus, so instead of u minus x, because everything is symmetric, so I don't have to do it all over again. It's going to be similar, only changes the role of x and y and z. So, and then you get the 5 over 2, and for the third term, mz 1 minus w minus y, same thing, over 5 over 2. So that's your curl. Let's take out this 5 over 2 terms, and then what happens for the rest of the term is that it's the sum and subtraction. So sum of let's see here, the 1 and times 3 of m vector here. So if you just take the first component here, mx, mi, and z, that's m right here. And then these are also the scalar number, so you can take out everything. So it's minus of m inner product u minus r, and the rest of the part is just the u minus r here. Divide by 5. I did 5/2. Okay, so that's your formula. So you can see that they're actually the same. All right. Yeah, so they're the same thing. So you can compare right here. So this is when I set my u to be 0. So it's a little bit simpler, but you can get the same thing just comparing these two. All right, so let's talk about the code a little bit, and then I'll take the questions. So let me start from here. So this is the entire code for the game. So there are some aspects that I implemented in the game. First, there is a space. If I press space, then it makes the streamline. And if I scroll mouse wheel up or down, then it makes a zoom in and out. And I can also click the mouse button to make my change of position of green dot here. So for the scaling, I made a modification key and option for that to make to check whether the modification keys are pressed. If it's pressed and the mouse wheel button is pressed, then I scale up or down. And then whenever I change the scale, then I redraw the dipole. I actually clean up all the screens here. And if I press the space, what I do is I used Euler method to find the trajectory numerically. And when I press the mouse button, left mouse button, then I draw my object, the green dot, in a new position. So whenever I change my position, I need to interchange my XY coordinate to the XY pixel coordinate of the screen. So I draw the object. This is not drawing actually. It's erasing the object that is existing in the previous frame, and I draw the new object in a new position here, in a green color, 0 to 550. And when the space is pressed, I can instantly draw the trajectory, but I made a little bit of animation so that when the space is pressed, the move is now activated. So also counter is set to 0, and at each frame the counter is increasing by 1, and it stops when the counter reaches to the maximum, and it draws the field lines at each counter up to that counter, so that it can see that it's actually the moving or trajectory is it's animating in some sense. And then that's everything here. So I need lots of other program, but I'll show you how it works first, and then if there are any questions, I'll take some. So let's see. Okay. So I can zoom in and out. Okay, so it's too small. Okay, zoom in, please. Zoom in, please. Okay, so I think it's a little bit work in the other weird way with the mouse pad. So anyway, so if I press space button, you can see that the trajectory is making here. So I can click the mouse button to change my position here, and then click the mouse button here. So if you can actually do it continuously, just changing the mouse button, changing the the position here, and then do it continuously to make a trajectory line. So in some sense, you're making a stream plot manually here. So that's not really what I intended to make. I tried to make it into 3-dimension and it was too complicated, and I made it into 2-dimension, and it turns out that it looks like as if I put the iron powder around the magnet. So I made a game name magnet, iron powder. So there are some aspect that I didn't intend it to, but because when I change my cursor position, what I do is I erase by redrawing the circle at the current position by the white circle. So when I change my points here, position of the point, then it actually erase everything, even the dipole point here. So you can do something about this by changing the code a little bit, but I just want the code as short as possible. So this is what happened. So you can actually redo everything here by zooming in and out. So you can do the drawing. So you can see actually that the numerical solution is always the same. The initial conditions are the same. So in the code that I made my Euler method to where about right here. Euler method to run through 0 to the maximum time, and maximum time is set to 100, so it's always the same. But when you go farther from the dipole, then you can see the trajectory is actually shorter than one that closer to the dipole. It's because you have a smaller vector field. The size of a vector farther away from the dipole is smaller than the one that is closer to the dipole. So that's why you don't have a longer trajectory here. But actually that makes sense, because further you away from the dipole, you have a less magnetic field. So you can take this as some insights to your project, the second project. So you can either visualize this dipole, or you can visualize other things like electric field. You can also do that. In the electric field, you don't have to put a dipole situation. You can have lots of charges in the different position to see whether that charges could generate electric field, not orthodoxical way. So just imagine what you can do about this. So that's basically it. And do we have any questions about today's discussion? No? Okay, so if no question, then we can call it here. Make sure that every group member appears next week class on Wednesday and Friday, and also make sure that you prepare a lot, especially for presentation. And also, you have to put your presentation material to the Notion site before presentation day. So I'm going to close out all the editing before we have a first presentation. And yeah, so the report is similar to the first one. You have to submit individually or by a group. And I'm going to upload the new template. You can use the same template as I uploaded before. As soon as I have uploaded the template, I'm going to open a new assignment page
to submit so that you can submit there. All right, so see you next Wednesday. If you have any questions, let me know before you go. And otherwise, have a good weekend, and then make sure that you prepare your second presentation